All right, so here is the first video from our next unit, which is comparing the distribution of two different populations. Everything now we've been sampling from a single population. And in this unit, we're going to sample from two different populations and say, hey, are these two populations the same, or are they actually different? And also, let me apologize. I'm tired. I've been doing grading. I've had way too much caffeine, so in today's video, if I seem a little strange, that's because I am. All right, so what we're going to be talking about is taking two different populations and if we take a random sample from each population, is there a way to say that these two populations are the same, and are they different? And so what we're going to start by looking at is, what does the sampling distribution look like when we combine samples or compare samples of two different populations? Because remember, all the theory for all the stuff, the confidence intervals, the significance testing, is all based off the idea of significance testing is based off sampling distributions. All our theory is based off the idea of, in a sampling distribution, what's the chance that we would get this? So, in Chapter 7, we saw that the sampling distribution of a sample proportion has the following properties. It's approximately normal as long as n times p and n times 1 minus p are greater than 10. The true mean of all the samples was the proportion in the population. And the spread of the sampling distribution was p times 1 minus p over n, as long as we didn't sample more than 10% of the population. So, to explore this, let's talk about, we're going to sample between two different schools. Each school has over 2,000 students. At school 1, they're all doing 70% of their homework did their homework last night. At school 2, 50% did their homework last night. All right, we're in God mode. We know that. So P1 equals 0.7. P2 equals 0.5. That is the true proportion. But we're going to look and say, hey, what happens if we sample from these two populations? So at school 1, they take an SRS of 100, and at school 2, they take an SRS of 200. Each school has over 2,000 students, so we sampled less than 10%. So what can we say about the difference? What is the difference going to be? What is the sampling distribution of the difference going to look like? And so when we do this, here is, right here, the approximate sampling distribution of P1. So the center was right what we said it should be, which is 0.7. And the spread is exactly what it should be, which is 0.048. For P2, and this is the slightly smaller, or we sampled slightly higher, we still see the shape is approximately normal, and the center is 0.5. And the spread is this 0.034. So that's exactly what we would expect. So let's talk about the difference. Now the difference is we're going to take a sample from population 1, and we're going to take a sample from population 2, and we're going to calculate the difference. Now, the center is 0.2, and that makes a lot of sense, because 0.7 minus 0.5 equals 0.2. But the spread, if you'll notice, got slightly larger. So even though we were subtracting the differences, the spread went up. And we talked about this earlier in the year, is if you think about it, this is a random variable, and this is a random variable. And so we're combining two random variables, and so the variability, if we're combining them in any way, adding or subtracting, is going to cause them to slightly increase. So where does this number come from? Well, if you remember way back when in chapter 6, we said if we combine any two independent random variables, then the difference of their centers, the average difference was the difference of the averages. But the variance of the difference was the sum of the variances. And remember, variance is sigma squared. If we take the square root of that, then we have the population standard deviation. So if you remember, we had to square them, add them, and then take the square root. And so that's what we'll find here. And we can go back to our example. If you square this and add them together and then take the square root, you get this. So when we just look at the sampling distribution of the difference of two samples from two different populations, the shape is going to be approximately normal as long as all successes and all failures are greater than 10. So when you check this, you're going to have to check not just, you're going to have to do N1P1 and N2P2. So you're going to have to check it not twice, but 4 times. The center is easy. The center is going to be the difference. But the spread is going to be this, which was something that we were taking the square root of before, and now we're adding them and then taking the square root. The good news is that this is on the formula sheet, so we don't need to stress about it. So here it is. If we take a sample from each population and we do a subtraction, we get a value. And we keep doing that, we keep doing it, we keep doing it. Eventually the shape that will emerge, if we do every single possible sample, is the sampling distribution. And so the center is the difference in the two populations. And the standard deviation of the sampling distribution is given by this equation right here. So now we can create a confidence interval. If we take the sample from two different populations, it's easy. The statistic, we go back to our familiar formula for confidence interval, which is statistic plus or minus critical value times the standard deviation of the statistic. Well, the statistic is just merely going to be p hat 1 minus p hat 2 plus or minus z star at the confidence level we choose, generally 95%, times the standard deviation of the statistic, which is this bad boy right here. So here it is right here. So our overall formula for critical value, our overall formula for a confidence interval when we're doing the difference in two proportions is this. And so when we're doing this, and pause this and read that through and read all the stuff and read the accompanying section in your textbook. But the key here is that if, let's say we did a poll. We said, hey, in 1990, this percentage of people thought the internet was important. And in 2010, we thought this percentage of the people was important. Well, we can't ever really say what the difference is because they're samples, but we can estimate approximately what the difference is, and that's what the confidence interval is. So this is where we're headed. So remember, you have to, if you create a confidence interval, you have to check the conditions for that confidence interval. They have to be random. They have to be normal. So you would have to check random. You have to randomly select from the population. You have to check the conditions. So you'll end up with 4 numbers, and they all have to be greater than 10. And you can't sample more than 10% from either population. So you have to sample less than 10% of both populations. And then when you do that, you get this formula. And so when you do this, it's going to be that same 4-part process that we did in chapter 7 or chapter 8, whatever the chapter on confidence intervals was. And what you would see is that it's exactly the same process. It's just that our formula slightly changed. But you're still going to state what you're going to do. You're going to check conditions, which is the planning stage. Then we're actually going to calculate the z-value, which is the do stage. And then we're going to conclude. Right? And we will conclude in context. We'll conclude with our confidence interval in context. So tomorrow in class, we're going to be exploring all of this. We'll be doing it during Flex and during the regular class. So that's it. Everybody have a nice day.